Good morning, everyone. It is my pleasure to introduce here the seventh Deeptails seminar that will be given by Shlomo Chazan and Sharon Gannot. Sharon is a professor in the Faculty of Engineering at Bar-Ilan University. He is the vice dean, and he is also the head of the Acoustic Signal Processing Lab that started in 2009. And since then, they did a huge amount of contributions on audio and speech processing. Some of them will be presented during the seminar. And Sharon will be presenting together with Shlomo, who recently earned his PhD from Bar-Ilan University, and who is now holds now a double position. He's the head of the speech and audio at the Origin AI Research Center, and he's also a postdoctoral researcher with Sharon at the Faculty of Engineering of Bar-Ilan University. So Sharon and Shlomo will present a talk that will discuss several works. And the title is Divide and Enhance Mixtures of Gaussians, Phonemes Experts in Speech Enhancement. So Sharon, Shlomo, the floor is yours, and we are really looking forward to hearing.
Thank you very much for the introduction, and thank you very much for the invitation, and for all of you for joining. We will discuss single microphone speech enhancement algorithms today. And all of them are under the umbrella of what we started to call divide and enhance, in which we break the problem into several smaller problems and solve each of them together and then merge the solution. So we will introduce the development of this concept from our early work towards our recent work. So in general, we are talking about single microphone speech enhancement. Namely, there is one speaker speaking, there is one microphone that acquires the speech signal, and this is done in a noisy environment, like with air condition, perhaps with multiple speakers, like in a pub or something. We will even play sound file recording in a pub. And this is, and the goal will be to retrieve the original speech signal as good as possible from the noisy signal Z of T. So a very, very brief history of this topic, which has thousands of papers and started in the early 70s. I would say that the entire discipline of single microphone speech enhancement was dominated by model-based algorithm. I would say that the most important work in this domain is by Phoneme from '84. They even recently won a prize for a sustained impact paper for their contribution. And most of them use some type of statistical modeling of the speech signal, usually in the short time Fourier transform domain. And from this, they developed the algorithms. What we have done together with my advisor in 1999 was actually a data-driven approach. So it still maintains the model in a sense that we have mixture of Gaussian. However, the speech signal is modeled based on data. So we have a huge amount of data, which not huge at the time, but quite large, from which we infer the mixture of Gaussian parameters. What we did more recently when Shlomo joined the group is to replace one after another all blocks of the system with DNN-based systems. But still, we would like to maintain this structure of splitting the problem into several problems. And this is what we'll try to explain from the roots of the '99 paper, which I will present, towards the more sophisticated stuff that Shlomo will present about replacing the blocks of the system with more advanced blocks, deep learning advanced blocks. So this will be actually the outline of the talk. So we'll talk about these four papers actually, and they are all forming one line, or they all can be seen as under the umbrella of divide and enhance. So let's start with the original work that actually started from a work on robust automatic speech recognition. In this work, we are working in the short infrared transform domain, and then taking the log spectrum, so absolute value log, and we replace actually the original signals with these features. Of course, only z of k we measure. Based on the fact that z of k is a summation, this is power spectral density, it's the summation of the contribution of the speech and the contribution of the noise, we can see quite clearly, due to the fact that the exponential is a very steep function, that actually in the log spectral domain, z of k becomes the maximum between the contribution of the speech and the contribution of the noise. So each time frequency bin is actually dominated, or the log spectrum each time frequency bin is actually dominated by a single region, either speech or noise. This will be very important for developing the models, and actually this is one of the reasons why people are applying binary mask or some type of other mask in order to enhance or separate signals. So as I didn't say yet, but we call this algorithm mix max. So the max was in the previous slide, and now I talk about the mix. The mix is a Gaussian mixture model, which you can see here, in which we take a database of speech signals. At the time, we took TIMI database. Shlomo will talk about it later. And from this database, we applied an unsupervised approach, actually just an EM algorithm, in order to cluster the speech signal components into the speech signal, log spectrum of the speech signal, into several components. I think we used something like 30, 40 clusters, and the model became a Gaussian mixture. All the parameters of the Gaussian mixtures, namely the mean, the variance, and the weight of the Gaussian per frequency, Fik is per frequency, was inferred from the data. So this is why it is one of the first contribution in data-driven modeling of speech signal.
Sharon, can
Yes.
I interrupt just to ask a question, just to make sure?
Yep.
In the notation, k is the frequency index, and here you do not represent time, right? It's just independent vectors.
Yes, since we take the entire database, actually, it's few hours of speech signal, and these are, let's call it the building blocks of any speech signal from multiple speakers. TIMI is also multiple accents in American English. So this is a representation of the speech signal in general.
Yes.
It's not related to the specific time frame in which you are applying the algorithm.
Yes, but in practice, I suppose you work in the time frequency domain, and in that case, a vector X is a slice of a speech spectrogram.
Yes, exactly.
Okay, thanks.
And then you cluster many of them. So all the R's are clusters to the same cluster in a sense.
And they are
Actually, Shlomo will present like a panel that shows that all R's are similar somehow.
okay, and they are considered independent.
Yeah, but what is, this is correct. What is important to say here is that the supervision is fully unsupervised. So we don't say, and we don't claim, this is one of the drawbacks, that all Gaussians are related to phonemes of the speech. This we will utilize later.
Okay.
But not in the original work. For the noise, it's very simple. We take part of the signal, let's say in the beginning, in which we assume that there is only noise, and assume that it's Gaussian, and we calculate the mean and variance of these frames. Now, since we are talking with the maximum assumption that I discussed before, then we know, since we know the probability density function of the speech, Gaussian mixture, of the noise, Gaussian, we can estimate the probability density function of the maximization, well known from probability theory. And based on this, we can calculate, it's a bit of tedious work, but eventually we get a very simple and intuitive equation saying that the estimate x of k is actually, here is the divide per class. This is what we call divide. And then we enhance each class separately. And eventually, after playing a bit with equations, we get this rho of k, which we call speech presence probability, since it decides for each time frame if it's dominated by speech or noise, softly decides. And if there is no speech, we do some type of conditional expectation that we'll discuss later. So the entire SPPs actually can be split into per class SPP and the probability of a class. All of them are inferred from the model that we just discussed. So this is the model, like to summarize, this is model-based, however data-driven. So this was the new concept that we introduced in this paper. It's completely unsupervised generative approach in the sense that we take into account the probability density function that are inferred from the data, which are quite general. And this is the main stuff here that we divide and enhance. As actually I just commented, we ignore the phoneme structure. We do not treat the residual noise very good, and we do not update. So we assume that the noise is actually fixed. The statistics of the noise is fixed from the start. So from this point on, you'll go to the more interesting part of the talk that Shlomo will present. And then he will gradually get rid of the generative model and replace it by deep learning models.
So as a short recall, we mentioned three main drawbacks of the mix-max algorithm. The phoneme structure of the speech is not taken into account. This is the first one. The second one is that even that it is optimal, the mix-max algorithm is optimal, the algorithm add noise to the enhanced signal. And the final drawback is that the noise statistics are not updated all the time. So therefore, we present the phoneme-based mixture of Gaussian. Before, we use the EM algorithm, which is an unsupervised method to estimate the clean mixture of Gaussian parameters. And therefore, we had to use the Bayes rule. So now we want to use the phoneme information to build the mixture of Gaussian in a supervised manner. So each phoneme will be, each Gaussian will be a phoneme. For that, we are using the TIMI dataset, which is a phoneme label dataset. It is constructed with 462 speakers training set and 24 speaker at the test set. And we used the 39 phoneme partition, which is the most common one. So as you can see below, for each time frame, we have the labels of the current phoneme. So even for the non-speech frames, we have a phoneme, which is the silent phoneme. Okay, so for example, if we take the phoneme A, frames, which was used by different speakers and different words and different recordings, and we concatenate them, we can see in the figure here that indeed they are they have the similar speech pattern. Then for each frequency, for example, if we are concentrating on the k equals to 62, we find the mean and variance of that frequency, and we build the phoneme-based mixture of Gaussians. This is carried out for each one of the phonemes. Now that each Gaussian is a phoneme, classifying the correct Gaussian is actually a phoneme classifier. This is the classification. In the generative approach, we use the Bayes rule, but this approach has some drawbacks. First, it requires noise statistics, and the second one is it is carried out independently for each frame. We propose to use a discriminative approach. Since it's a classification task with labels, we want to use a deep neural network for that task. The DNN doesn't need the noise statistics, and it can save the continuity of the speech. So we want to switch between the generative approach or the generative rule-based approach to the discriminative deep neural network classifier. The hybrid approach, we call it still a hybrid because we are still using not all deep neural network architecture. So first, we find the speech presence probability given that we're in a specific phoneme and given that phoneme Gaussian. This is carried out for each Gaussian. And then we found the phoneme probabilities with the trained deep neural network phoneme classifier. And finally, the hybrid approach merged the generative SPP, speech presence probability, with their corresponding discriminative probabilities, and we found the final speech presence probability, the final SPP. Until now, we took care of the phoneme structure and the generative approach. Now we want to fix the residual noise that we speak about drawback earlier. As a reminder, speech presence probability is rho. So, and for each frequency bin, we apply the following enhancement equation. If it's speech, we leave it. And if it's not speech, we go to the Gaussian and bring the information from there. Although it is optimal, it might not be the best solution. Okay. Okay, for instance, if we are looking at the lower left picture, this is the speech presence probability. The yellow indicates the active bin, the active time frequency bins where the speech is, the speaker is active, and the blue one is where the speech is not, the speaker is not active. So in between the harmonies here, there is no speech, and what the residual noise approach is doing is go to here, which is the this part of the equation, go to the Gaussian mixture and take the information from here. And of course, this is we add the noise. If we know that the speech is not active in that frequencies, we need to lower this energy and not bring additional noise from the Gaussian mixtures. Therefore, we developed a new enhancement equation. The speech presence probability is used as follows. So if it's speech, we want to leave it. And if it's not speech, it's only noise. So we want to attenuate the observed noisy signal with beta, which is the attenuation level. Okay, so finally, the speech presence probability is calculated also with the current parameters of the noise. And since the noise can be non-stationary and can change in time, we have to update it in all the time. Currently, the Mixmax algorithm does not update the parameters of the noise Gaussian. The speech presence probability is the probability that the speech is active, but 1 minus the speech presence probability is the probability that the noise is active. So we can use this information to update the noise parameters as follows in these equations. Here we update the mean and the variance of the noise Gaussian. So to sum up, the phoneme-based mixture of Gaussian main contributions are, we took into account the phoneme structures of the speech. The residual noise was also fixed and subtracted. The noise statistics was updated all the time. But on the other hand, it is still a Gaussian model and it is still a generative approach. Only the phoneme classifier is discriminative. This brings us to the This brings us to the mixture of phoneme experts algorithm. So if we want to be all discriminative, we can use an all deep neural network approach. The most common approach is training a single deep neural network to estimate the speech presence probability. So the input to the network is the noisy log spectrum together with some context frames, and a single network is trained to estimate an accurate speech presence probability. This is a discriminative approach, and it does not require a model for the speech. So this is the good stuff. But on the other hand, a single network has to deal with the high variety of the speech structure. And once again, the phoneme structure is not taken into account. And finally, it requires training on many noise types. This brings us to the mixture of phoneme expert architecture. This architecture consists of 39 phoneme experts, which are all deep neural networks, and a gate deep neural network, which is a phoneme classifier. This way, each classifier has a much easier task, and the phoneme structure of the speech is preserved. We found that it doesn't require training on many noise types, and it is still robust to different or unknown noise types. For that, we first pre-train the architecture because it's a complicated architecture. This each phoneme deep neural network, which we call PDNN. So each phoneme deep neural network was trained separately with its own noisy phoneme dataset, and the gate or the phoneme classifier was also trained separately on the noisy dataset. This time with all the phonemes, of course. But there is a catch. In the test time, the phoneme classifier might be mistaken. And so in that case, the wrong expert will be activated, and of course, the performance will be lowered. Therefore, the just pre-training is not sufficient. Okay, so for that, after the pre-training phase, we jointly train the whole architecture together. This way, the entire network is forced to learn also the mistakes of the phoneme classifier. And the final row, this is the main thing that we are going out with. Okay, so to sum up, we have 3 phases. The pre-training phase, in which each phoneme deep neural network is trained separately, and the phoneme classifier is also trained separately. In this phase, the phoneme labels are known and used. In the training phase, or the jointly training phase, the system is trained together, and the phonemes are known but are not used. And of course, in the test phase, the phonemes are not known and they are unknown. All the system's components are used to find the speech presence probability, and we then carried out the enhancement as we have shown earlier. And okay, so this approach has some drawbacks of itself. So first of all, it requires a phoneme label dataset, of course. The second one is the phoneme-based partition might be too restricted. We have 39 numbers of experts, yeah? And it might be that a different partition of the speech variability, maybe with an unsupervised manner, might be beneficial. Therefore, we present the final algorithm here, which is the mixture of deep experts, or the self-supervised mixture of deep experts. As you can see, it consists of M experts. Each expertise, for now, it's unknown. We can understand it only after the training. And we have a gate again. So theta comprises of the parameter set of all the network, which is the gate network and all the M deep neural networks. M is different now. Earlier it was 39, or the number of the phonemes. Now it's also an unknown number. And the best M was chosen with a greedy search. So it's a complicated architecture. We could randomly initialize the mixture of deep neural networks parameter, but we found out that it's insufficient because it tends to utilize only few of the experts. Therefore, we had to do a pre-training stage. But for that, we needed a supervision. Since we do not have the supervision, we chose to use a clustering approach, which is taking all the clean signals, EX, and train a deep neural network and on the autoencoder. So the output is also X hat, and the embedding, we used it for applying the k-means clustering algorithm on the embedding. Then we found M different patterns of the speech in the log spectrum domain. Note that we used the clean signals and not the noisy signals, because we encourage it to focus on different speech patterns and not on different noise types, which could have happened if we used the noisy signals to the clustering. Once we have the labels of the clusters, we can use it to pre-train each component of the network separately, as we did with the phoneme mixture of phoneme experts. Now the joint training is using this loss, which is PI is the gate probability, or the expert probability. D is the distance, which we chose to be the mean square error between the estimated the true speech presence probability and the estimated ith SPP. And in this equation, we do not encourage collaboration between the experts. So in a test time, each expert will be, we want it to be the only one who is, the output is carried out from him and not from the others. And of course, not from collaboration of each one of them, because then all the structure is not is just a big neural network. Okay, so finally some results. So in the experimental setup, we've compared ourselves to 3 more networks. So the first one is deep single expert. We wanted to see how much the divide and enhance is better than just taking one expert. The second one is a supervised mixture of deep experts, which is the mixture of phoneme experts. And the third one is the mixture of deep expert, which is the self or semi-supervised mixture of the deep expert that we've mentioned at the last algorithm. Note that all methods consist of the same number of parameters for a fair comparison, and the results that we will present with the mixture of deep experts are obtained with M equals 5 experts. So note that we reduced the number of experts. We started with 40 at the Gaussian mixture, and then we once we've used the phonemes, it was 39, and now we are using only 5 experts. Okay, so the data set was trained, all of them were trained on the Timmy data set with this noise and random noise with SNR, which was randomly chosen between -5 and 5 dB. And in the test set, we used the Timmy test set and the Noisix 92 data set with these SNRs, and we will present the PESC and some wave files. Okay, so the first one is the PESC results. The PESC, just to be sure that we are speaking at the same side, the PESC is the mean opinion score between 0 and 5. The hard blue is the noisy, the light blue is the deep single expert, the green is the supervised or mixture of phonemes experts, and the yellow one is the mixture of deep expert, which was only with 5 experts. So as you can see, there are a few interesting things here. So the first interesting thing is that the supervision is already better than, sorry. The supervision is already better than the single expert. So the divide and enhance is a good approach. And then what it's more interesting is that even that we have the phoneme information in a non-supervised manner with only 5 experts, that we can not know in advance which of the phonemes or what went to each one of the experts, we gain even better results than the phoneme class, the mixture of phonemes. Now after we trained, we want to understand or to gain better understanding on the expertise of each one of the experts, and also to understand what is the gate does. Okay, so this is the input, the noisy input. This is the output of the gate, and this is the output of the 3 experts, expert 1, expert 2, and expert 3. And finally, we sum up all the experts' outputs with their probabilities from the gate, and this is what we finally get. So the first interesting thing is to know that this expert only, or this expert expertise is the high frequencies, the unvoiced. And this one is the exact opposite. Only the low frequencies and the high frequencies are not good. This expert is like a voice activity detector. It knows when there is no speech, and therefore in that frames, you can just go lower everything. The second interesting thing is the gate output. As you can see, that the sum of each frame is summed to 1. And as you can see that in each frame, it's very certain of itself, and it is smooth in time, and it's also very sharp. So eventually we can gain even a complexity reduction, because no matter how many experts you have, eventually in the test phase, you just apply the gate and then one of the experts, even if you have 10 experts. So you gain a complexity.
Sorry, can I interrupt to ask a question?
Yeah.
Here you represent 3 experts, and you said that you are using 5, right?
Yeah.
Are you just representing 3 out of 5, or are you using an expert of 3 experts?
Here I'm using a mixture of deep experts with 3 experts. Okay. It was trained with 3. With 5, the resolution is even higher, and it's more complex to understand what is the vision, or what is the expertise of each one of them. Okay. But with 5, but after 5, let's say that after 5, we have got some kind of saturation in the performance.
Okay, thanks.
Okay, so finally we can, I hope that you will be able to hear it. This is a crowd noise. This is the observed noisy signal.
Sickness kept him home the 3rd week.
Okay, and this is after we have applied our algorithm.
Sickness kept him home the 3rd week.
Okay, this is a different kind of noise.
The meal was cooked before the bell rang.
And this is after.
The meal was cooked before the bell rang.
Okay, Sharon, you will take it.
Yeah. So just to wrap up, we actually started from our 99 work in which we used mixture of Gaussian, data-driven. However, the algorithm was still model-based after inferring the parameters of the model from the data. Then we gradually replaced blocks with deep neural network blocks. The first one was replacing the phoneme classification with a deep learning-based phoneme classifier, and each of the Gaussian was clustered based on the phoneme structure that we know for English for sure. And then we decided that we don't need anymore the models. So this is why we went to a full deep neural network architecture that are using mixture of phonemes. Still, we need the phoneme classes. So we should have a very detailed labeled speech database, which only exists in English, as far as I know. And then we moved further towards a mixture of experts in which each expert becomes an expert in one block of the signal. The line or the tail, let's say, from the early work till the recent work is the fact that we take a problem, which is a complicated problem, split it into or divide it into several smaller problems, and each of the problems we solve, and then we combine them based on some type of management of the system. So this is why we call it divide and enhance. I think this concludes what we wanted to say, and we hope to have some discussion now.